The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney. Welcome back. Today we have Dr. Cassandra Grenade, who's the author of Learn Quantum Computing with Python and Q# from Manning Publications. Such a great shop. I love their books. She's also the owner and principal of Dual Space Solutions, LLC, and is a prime contributor to the fascinating project of the QIR Alliance. And we'll be talking about that at some length today.
Right. Kevin, quantum intermediate representation is what that acronym expands out to. This is a really, really interesting project, open source, open standard project that the QIR Alliance is driving, that Cassandra is one of the prime movers behind. And the work that they're doing is to create this intermediate representation that's meant to promote better portability of code in the quantum space. An intermediate representation is a way to provide a middle ground, if you will, between the lower level of the stack, the hardware, hardware-specific functionality, and the higher end of the stack, the higher level languages, the general purpose languages, things like Python, Rust, and the like. So it's a really interesting topic. It's become one of sort of the hot topics within the quantum information science community. And I'm really interested to hear more from Cassandra. Welcome back. We are joined today by a special guest, Cassandra Grenade, who an independent consultant in the quantum space with quite an interesting professional path and academic career in her background. And Cassandra, would you mind, thank you for joining us, and would you mind introducing yourself and give us a little bit of idea of how you got to where you are today?
Absolutely, and thanks for having me. Wonderful to be here today. As far as how I got to be where I am today, that's always a fascinating question.
Isn't it?
And in part because I think I got to where I am, that followed the particular path I did by virtue of being very, very bad at making decisions about what I want to be when I grow up.
Oh my gosh.
I go back to undergrad, and I did the very unusual thing of a triple major because I couldn't make up my mind whether to do math, physics, or computer science. And 7 years later, never did make up my mind.
Which happens to perfectly describe the intersection that you need for quantum information science, right?
Perfect. Exactly. Yeah. And so, it's like, well, where can I apply all three of these? This quantum computing thing looks pretty good.
So convenient.
Yeah. But so from there started with grad school at Perimeter Institute, was one of the inaugural year of Perimeter Scholars.
Wow.
And that was really neat, had a lot of different perspectives that I wouldn't have ordinarily gotten, I think, coming through kind of a sort of quantum computing focused or CS focused or even pure physics focused. It really was a lot more interdisciplinary.
Yeah, it sounds like a cool scene. Yeah, no doubt.
Yeah, absolutely. Went from there to do my PhD at U Waterloo before doing a postdoc at University of Sydney.
Cool.
And from there decided to come back to the US to join Microsoft. Was there for about 5.5 years. And recently made the move to be independent and launch my own consultancy. And that's been a lot of fun.
That's Dual Space, right? Is your consulting? Dual-space solutions? Yeah. And is there anything in particular that you're trying to focus on with dual space, or is it fairly broad, or how would you characterize your offering?
My joke around that is always, my niche has long been not having a niche. See above about, being very bad at deciding what I want to be when I grow up. That's all the cheeky and humorous way to put it, but the more serious answer is my strength across my career has always been taking an interdisciplinary approach, being able to find, what part of a problem is not being seen, what's missing, and try and go explore that part. And that's what I try to bring with dual space solutions as well, is to not say define myself into a particular niche, but rather to be able to say, if you have some broad strategic question, what are you missing? If you're trying to look at some program as a whole, where are the parts where maybe you're not taking into account culture and workplace or community, maybe you're not taking into account sort of some classical computer science bit that, there's a communications breakdown between the sort of CS or physics mindsets around things.
Sounds really cool. I mean, I've done some of the solo consulting stuff in the past, and it can be, a complicated thing to run. So, respect. That's impressive. I was just wondering, Cassandra, could you give us a little bit more detail about the nature of some of your engagements that you're doing? It sounds really interesting.
Yeah. So, I mean, it is fairly new. So I've been doing this a few months as an independent consultant now. And I think where I'm most excited to look is, sort of collaborating, as mentioned, around, finding places where existing expertise at a company may not cover everything, and where I can try and provide some of that context. And for that, I do bring my PhD and postdoc were around software for statistical characterization, so QCVV. And that brought a lot of software focus to doing physics experiments. A lot of my work at Microsoft was, kind of connecting research ideas to software implementations. And that's the same kind of expertise that I bring now to solo consultancy work, is trying to connect some of those two across. So a kind of discussion I really love having is, hey, here's an interesting research idea. How do we take and put this into software? Or here's some software. What are we missing in terms of the research context in which that software will be used? Or, here's some classical computer science idea. What's wrong with it about, as we generalize that to quantum? Or alternatively, and arguably more importantly, what's right? What do we not have to throw out about classical software history as we're coming to a quantum context? So, I mean, from all those different perspectives, what I'm really excited about working with, folks across the industry is finding places where those connections aren't happening, or maybe they are happening, but, the outside perspective on the collaboration is still really helpful.
Right.
Yeah.
Right. I mean, I joked about, that's the perfect sort of set of disciplines to intersect to create quantum computing. But that is really true in a way. I mean, that interdisciplinary perspective is particularly valuable at this stage of an emerging technology, when in large part we don't know what we don't know, and it very rarely is the best strategy to just sort of assume, based on priors, I know how to approach this problem, and I'm just going to wade in and treat it like previous contexts that I'm familiar with. And often you need that kind of outside perspective, bringing in some unexpected viewpoint or some tool that you are lacking in your toolkit. So that sounds like a really valuable approach.
No doubt.
Absolutely. And I think across the field, we are seeing a lot of places where that is necessary. There's also kind of the opposite of, sometimes things are a little bit different in quantum, and we need to know when to throw out bits of history, when to keep them. And I mean, I think the two most dangerous things modes you can get into is, quantum is just, like classical computer science, so we know exactly how to do that. Or quantum is nothing like classical computer science, so let's throw out everything we've ever learned. I know it's kind of cliche and everything to talk about how weird quantum mechanics is. I think it really isn't as weird as all that. There is a lot we can learn, but occasionally there are things that we really do need to rethink something classically. And the challenge is being able to really tell the two apart. How do we act judiciously and, really pick out the parts of classical computing history that are essential to keep, that are really going to save us a lot of reinventing the wheel. And I'll say, I think that's somewhere that like physics as a sort of curriculum, less than an industry, less than a discipline, but, if you talk about physics majors, that's somewhere where I think a lot of students are really let down, and it's causes a lot of reinventing the wheel.
Sure. Yeah.
Throw out the wheel if it's not working. Like, I'm not trying to say we should be constrained by history, but if you don't know what you're throwing out and you're not doing it on purpose, then it's really easy to kind of reinvent the mistakes instead of adapting to, what's unique about your situation.
Right. So this is an interesting thread of conversation. I wonder, can we drill down? I mean, what major elements? I mean, our audience are many of them, really into tech or, the fast-moving advances within the sciences. I mean, what elements of classical computing tradecraft do you think are really important to preserve within quantum computing, and what areas and traditions are just get tossed out entirely? I mean, help us see the landscape as you see it.
So, a lot of my PhD and kind of postdoc, if I go into a lab, right, the vast majority of problems that I see people struggling with in a lab are software, right? Because now there's a giant caveat there. That's, some 10 odd years ago. And I think things have improved immensely since then. But it really used to be, well, okay, if it's not a software problem, then the people in that lab are well equipped to solve it. And so you see everything it being a software problem, not because that's somehow more foundational or it's more fundamental, but because people have solved everything else and that's what's left. And, it's a lot of, I think of kind of, the work I've done in language design and collaboration, things like that, or, how much of just writing classical software comes down to string handling or writing, boring sort of loading config files, saving config files, things like that, comes down to managing your source code, with things like Git, tracking issues. And that's a lot of the workflow that, again, I think isn't really part of a physics curriculum.
Right.
So it's always a stumbling block again when you kind of get to, oh, hey, my job is now also software because I'm managing a lab or I'm trying to. And so I think that is, there again, my comments are really about physics as a curriculum rather than physics as a practice,
I see.
And where I think students encounter stumbling blocks and work through it. I don't know, you stare at any piece of software long enough and it's a string handling problem, whether that's star IDN on some GPIB connection or whether it's, trying to export a plot and writing out graphics primitives. Like, you're still at some point doing the same sort of string handling that's been done since, well, computers.
No doubt, yeah.
And is that level of sort of abstraction from the perspective of CS, the discipline of CS, is that sort of where you came from when you started working on the subject I'd really like to dig into the most in a way, which is QIR, the quantum intermediate representation language? Yeah.
So, I mean, I really see QIR as a very radical attempt to not reinvent any more wheels.
Right.
Right. So if you talk about what a quantum program is, we've known since about 2005 as an industry, since before really we thought of it as an industry, right?
Right.
We've known since about 2005 that fault-tolerant quantum computation involves a lot of conditioning quantum operations on the results of measurements, right? And this comes about due to the demands of fault tolerance threshold theorem, that you're doing error correction, you're doing a lot of decoding, things like that. And there are certainly tricks and techniques, and we've learned a lot since 2005. I don't think fault tolerance in 2023 looks the same way it did in 2005. True. But the piece that I think is really important that we carry with us even now is that quantum programs aren't circuits. Circuits are part of quantum programs. That you have also all of this rich classical logic going about.
Right.
And decoders are, in general, fairly complicated compared to, the kinds of classical logic that we can write out with double lines and a circuit notation. There's some pretty simple decoders, but even the simplest are still going to look complicated compared to the control flow that looks nice in a circuit diagram. And so, that really does say, all right, we need a way to write down what a quantum program is. We know it has these classical elements. And as soon as you get to that, just throw out the quantum part. It's hard to write down those classical processing elements. People have tried for decades and decades to have a way of writing down a classical algorithm in some portable way. The promise of write once, run anywhere with Java. The idea is, and there we're pretty
triumph of marketing, you have to admit.
No argument. But, that's even in a case where we're pretty spoiled by the fact that most classical processors look kind of the same at the level of writing out, a block diagram and pseudocode. Yeah. The details are incredibly important, but I can still treat mathematically, an ARM core and an x86 core as being roughly the same in terms of there's an instruction counter and a program counter, and they proceed through, and it looks vaguely like a random access machine in both cases. And at the level of, writing down what a classical program is, those details matter a lot, but it means I can use the same kind of abstraction in both cases. And even there, it's been a decades-long problem trying to figure that out. And that's before I even allocate my first qubit. I have to have something that is at least as hard as this problem that's taken us, a few decades to have really good approaches on the classical side. And so the kind of radical not reinventing a wheel is, well, let's not do that. Let's just actually use the tools that the classical CS community has developed over those decades that, there's no perfect solution, but that work pretty well at giving you portable representations of classical programs across different architectures and across different CPUs. And, it's been kind of neat looking at how much the LLVM project has done classically, and that it first off decouples the idea of what a language is from how do I reduce code down to a given processor. But making that step has also enabled some pretty surprising things, like that you can target GPUs or FPGAs sometimes, or even target things that just would have been really weird to imagine at the start of LLVM, like targeting WebAssembly. For a little while, you could look to things like Emscripten for compiling C to JavaScript, which feels exactly backwards, but was really useful in taking some legacy code and making it available for folks to use in a web browser-driven world. And that's the kind of really surprising reinvention that I think was enabled by having a good point of handoff between front ends and back ends. So QIR really does build on that by saying, look, we're going to at some point have to write down a classical program, whether it's a decoder, whether it's, some repeat until success algorithm. So let's start with a baseline of something that can represent classical programs, and then build on top of that the things we really need for quantum.
So this is such an interesting thread, and we're in some sense just hobbyists and not experts like you. But we try to get close as we can, given our abilities, to what's going on in these underlying architectures. But it will be surprising to hear from you that the diversity, right, in quantum computing architectures can be sufficiently abstracted to fit into a broad enough framework. I mean, I agree with you that different CPU types in classical computing, there's one abstraction that can cover, virtually all of them. I mean, is it really the case then that the diverse array of quantum computing architectures can also be successfully abstracted?
There we're saved again by, sort of the fault tolerant threshold theorem, right?
Uh-huh. Yeah.
The whole idea of fault tolerance is in some sense is to abstract away what errors look like in your device. But that also means you're abstracting away the details of that device in particular and reducing it down to instructions that are, part of your error correcting code and so forth. I mean, that's part of why, things like the Clifford group have the importance that they do, is because the role that they play in kind of that fault-tolerant arguments and things like that.
So then, are you saying that? Sorry, Kevin. Does that? Am I right in thinking then that you're leaving the task of fault tolerance to the QPU, and you're assuming that input is sort of these idealized circuits that will then be implemented at the hardware level in a way that meets the fault tolerance threshold in whatever way is appropriate on that piece of hardware. Is that right?
So I'm not saying that. I'm in that in particular. I don't want to make a statement at all as to what happens inside a service provider in terms of how they take that. I know there have been talks, for instance, from like IBM where they've shown a little bit behind where, they accept input and what they do with it. And that does look, like you're saying, we've heard things like a successive lowering amongst different IRs. But, I'm certainly trying to stay agnostic on that and think from the standpoint of, what is a good point of interchange? Where is it that we can not specialize our languages, our compilers, our compilation passes, and our optimizers and things like that to one service provider, while still keeping the generality we need to really match, what we've learned from sort of 2005 era thinking, together with what we've learned about the importance of sort of near time, again, to borrow IBM's terminology, but the importance of near time processing adjacent to your quantum program.
Right, which goes back to your point about fault tolerance, error correction. They're going to need a lot of very tightly coupled quantum resources and classical resources to encode and decode and make decisions conditioned on the output of a prior circuit, right?
Yeah, and to take a little bit of a brief tangent by way of answering that, I think, where, we've seen a lot of really exciting things come out of near-term quantum devices is when they teach us how to build better quantum devices.
Right.
Now, there are many other exciting things about. I'm picking out the thing that excites me the most out of, which is, and so there, if you look at a lot of kind of near-term algorithms, they have this flavor of do a thing classically, do a thing quantumly, do a thing classically, do a thing quantumly. And, that there's this alternation between. And the tighter you can make that alternation, the less times you're, making round trips back and forth with a service provider, and the better everybody's life gets. That's another mode of integrating classical and quantum computation that I think wasn't really obvious in 2005, sort of early fault tolerance era, but now is a feature that we probably will expect to see carrying forward to larger and larger devices, in addition to that tighter real-time mode that you mentioned just now.
Right.
And just for the benefit of our audience, I mean, I could think of at least two examples, right, where that classical quantum interchange, right, is very common. One's, of course, quantum variational eigensolvers, right, and the other is all of these interesting algorithms where classical compute capacities are being used to essentially tune, right, an error correction algorithm for quantum computation. Are there other concrete examples of this sort of, for the benefit of our audience, on this classical quantum interchange which have broad application?
I do think you called out variational algorithms like VQE. I think that is sort of the quintessential place where we see that that alternation where there's classical processing that happens at a time scale that's long compared to qubit lifetimes.
Right.
Sure.
And then there's things that look more non-adaptive within qubit lifetimes. And I mean, variational there is kind of the clue, right? It's the word that says, I'm minimizing a function.
Yeah.
And everything about black box optimization in classical computer science, I don't really need to know what thing I'm minimizing to have that sort of alternating structure of I make calls into this thing, I look at the value and use that to decide where I call it next.
Yes. Yeah. Right. Makes sense. I mean, I gather there's probably also some quantum machine learning algorithms as well that do a lot of that. Yeah. Same kind of back and forth classical quantum alternation.
Yeah. So certainly not trying to say it's exclusive, rather kind of the opposite, that I think, what we see and what I think we really learn out of variational algorithms, and again, there's many exciting things, but the thing that, excites me when we're talking about stuff like QIR is like, well, okay, what do we need to take with us as we build larger devices, as we build toward fault tolerance? And, the insight that, yes, we have classical computation happening both at timescales that are long compared to qubit lifetimes and that are short compared to qubit lifetimes. Yeah, and we need some uniform way of representing both of those. That's the insight that I think is really important there, and really, really interesting when we're looking at both sort of 2005 style arguments, what we've learned about variational algorithms since 2016, and where we would like to be as we build out fault-tolerant devices as an industry.
And I have to agree with you. It really is a fascinating question, and really at the outer limit, right, of skill sets of two separate professionals who are well known for their IQ and their energy. I mean, amongst physicists, quantum computing is a no mess around subject. Among computer science people, compiler optimization is also the deep end of the pool. So you're doing two hard things at the same time with this rather ambitious project.
I mean, it's been a challenge in classical computer science to say, let me write down a description of a classical program that doesn't depend deeply on the details of any particular processor. That I can lower down to a processor as a next step. If I look before LOVM and things like LOVM, I think now LOVM has kind of won out in some pretty significant parts of that space. But, if I look before that, or at least before it was clear that LOVM was a good sort of industry consensus, if I have some processor that I want to run things on, I have to pick a language that is supported on that processor, right? Rather than saying, hey, I want to write a program and I want to use a processor. And the thing is, that's how the world looks now, today, in classical computer science.
Right.
If I look at embedded devices, right? So my partner and I, kind of as a hobby, we, like instrumenting our house with like different CO2 sensors, or putting telemetry on our boat and things like that. A lot of that is writing things, for different ESP32 microcontrollers and stuff like that. And if you look at sort of microcontroller role today, there isn't such a thing as the C language. There's the C language as this microcontroller company implemented, and the C language as this company implemented.
Yeah.
And the idea of C being a standard is kind of unheard of. They're all like, weird quirks about white space formatting that depend on and it's like, well, okay, I get the details between these different microcontrollers matter, but I didn't think white space was one of them, right? But it just becomes along for the ride.
String manipulation again.
Absolutely. So if you're writing a compiler for, your bespoke microcontroller, you're starting these days, it probably is going to look more like taking something like LLVM and writing a lowering step from LLVM-IR to the things that make your architecture unique, than starting with, well, let me first write down what a string is. I think that's where we really can learn a lot from classical computer science history there, and why, I think QIR is as exciting. There's a lot of differences between different quantum architectures, but there's also a lot that is in common.
Right.
And trying to start by abstracting over the commonality that we can.
Yeah, and if I could take another tag, so OpenChasm is sort of the existing, I would say, probably most used, most leveraged open standard for representing primitives on a QPU, right? The circuits, the gates. When you compare QIR to OpenChasm, does the difference boil down to exactly what you said before, that fault-tolerant quantum computing in 2005 was there's a different understanding of that topic then than there is now, and QIR incorporates our new understanding of that topic compared to OpenChasm, which is a 2005 version of what that looked like.
So I'm going to give two very different answers to that.
Okay.
Because it depends highly on whether you're talking about OpenQuasm 2.0 or OpenQuasm 3.0.
Okay.
I really do think those are very different topics as far as that's concerned. And we'll give you very different answers to that. And the 2.0 case, that's OpenQuasm 2.0 is a great language for writing down circuits with little to no classical control. Right? Things where the most complicated classical control you get looks something like teleportation or things like that. But where I can't really do anything like a while loop, right? That you might expect out of, say, a repeat until success algorithm. There have certainly been extensions to OpenQuasm 2 that try to allow that. You can take and loop unroll, but then you're paying a lot of overhead in propagating through those controls, and you have to have a very small, finite number of iterations that you can consider, and it composes really badly to do everything loop unrolled. Right? So OpenQuasm 2, it's a great language for writing down quantum circuits that are either entirely non-adaptive or have very little classical adaptivity. With things like OpenQuasm 3.0, we're starting to see, again, I think that industry consensus that we need a lot better representation for classical control reflected there as well. But, I'm both excited about OpenQuasm 3 and where, I do disagree with it some. I think OpenQuasm 3 is a great high-level quantum language. I don't think it's really what we want out of an intermediate representation. And the reason why is there's a lot of great high-level things like, looking at taking powers of a gate or looking at adjoints of a gate or controlled operations and things like that are exactly the kinds of conveniences you want in a higher level language to be able to efficiently write out quantum programs, but are exactly the kind of overhead that you don't want to think about if you're taking a already compiled quantum program and lowering it down to the specifics of a particular piece of hardware. And that's fine. Like that's in fact kind of the whole sort of game that we're trying to play here as an industry, is how do we take and abstract out the things we can abstract out and focus, tools on the things that they're really good at. To my mind, I really like seeing OpenQuasm 3 as a high level language. I think, it's great to see that there are more and more high level languages that do in fact have the capability for expressing some fairly sophisticated classical control algorithms. We see OpenQuasm 3, we see Q#, we see CUDA Quantum. There is a talk at Quantum Week about Xanadu's work with Riverlane along those lines. And it was great to see that talk. And then that, to my mind, increases the need to have some common sort of intermediate representation. If I'm, a researcher working on, some neat new circuit optimization technique, the last thing in the world I want to do is have to think about all of the nice high-level features that OpenQuasm 3 provides its users to be able to write out programs by hand. I just want to know, excuse me, this is the list of actual operations. And that looks a lot more like an IR. And I think that's part of why, you start to see a real stack, and OpenQuasm 3, I think, could be a part of that stack. But I think, if we're looking at intermediate representations that can handle the requirements we know both from kind of current near-term devices and from the sort of 2005 era fault tolerance arguments that have continued through to today, QIR is what we've got. There aren't really alternatives that deal with that at the moment. If there are alternatives that are developed, that's awesome. I don't think it's one of those where the first thing that we think of is always, the best or what'll carry on for decades.
Sure.
But right now, if you're looking to develop tools that can act on quantum programs in general, then I think QIR is looking like a really good choice for that. And I think that really opens the design space for languages. I hope we'll see more. I mentioned 4 different ones there. I hope we'll see more use the fact that, QIR does offer that nice point of handoff and start to really see more exploration of the design space for quantum programs that can include classical adaptivity.
This is just great detail. Thank you. And help bottom line this for our audience. I mean, in terms of the ultimate effect, right, on the overall ecosystem of coders and theoreticians and so forth that use these systems, where do you see the primary expression of traction, of benefit of the QR system? Is it developer productivity? Is it compiler optimizations? Is it better interchange and portability? I'm not sure. What's the primary effect?
It's kind of hard to talk about any of those without acknowledging or kind of giving voice to, I think, the biggest one of it just changes what we mean by what a quantum computer is. To look a lot more like the sort of scalable devices we hope to build instead of the really exciting devices we've been able to build for the past almost 10 years that have taught us an immense amount that we've been able to do a lot of really cool stuff with, but maybe don't have all of the architectural details that we expect things to eventually look like. So I mean, it's productivity and portability and interoperability are all things that I think are really great to have on the forefront of our minds. But there's the even more exciting thing to me of we're just changing what a quantum device looks like. As an industry, as our consensus sort of shifts and our capabilities in industry evolve to look more like what we need out of scalable, practical quantum devices.
And so, more specifically, that means you believe, I'm guessing, deeper and richer expression of error control and error correction, and these hybrid classical and quantum computing capacities more deeply integrated. Is that correct?
Yeah. So I think there's at this point a lot of good understanding at a mathematical level, at a practical level of having tried it and seen where it got us.
Yeah.
That quantum programs do not look like circuits. Right. Circuits look like subroutines in quantum programs.
Right.
That doesn't mean circuits are bad, circuits are useless, circuits are great, but they're subroutines, they're not programs.
Yeah.
And having something that includes everything we've learned about sort of pure circuits and can put that into the context of a full quantum program, that's the kind of infrastructure and that's the kind of architecture we need to keep going.
And help me with something else, Cassandra. So this is probably my mistaken framing, but Open Pulse was released with Open Chasm 3. And it feels like Open Pulse is a lower level construct than what you're talking about. When you said Open Chasm 3 as a high level language, I get it on the circuit and gate description level, but on the Pulse schedule level, that feels like a lower level.
That's fair, and it certainly, I think, kind of reflects my own interests in kind of where I'm sitting at the moment of that interoperability, that handoff between different architectures and everything like that. The pulses are exactly what you don't get to talk about when you're looking at something at that level of abstraction.
Right.
But it's a very fair point, and I'm not personally involved with OpenQuasm 3, so I can't, do anything more on that than sort of read the same documentation.
Well, I guess to ask the question more generically, so if you think about the era we're in right now, before you get to an idealized machine that you can assume is fault tolerant in some way, you may have to, do special things to handle the types of errors that your particular jar subroutines are going to encounter or whatever. But there's a lot of capability in the platform itself. Right now, you can think of all kinds of use cases where you may have to tweak at the lower level, like dynamical decoupling or something like that, right? I mean, there are ways in which you can use control, the actual control, the direct metal control in a quantum program as it exists today. Is that something that QIR would be able to manage within its context, or is it out of scope for QIR?
At the moment, my understanding is that is something that is kind of out of scope for QIR, just because, to your point earlier about, higher level versus lower level in terms of what properties of the device you're even looking at.
Right.
But, if that's... There are ongoing QIR community calls, and I hosted by the Unitary Fund.
Right.
And it is really interesting to follow those discussions, because sometimes, you join one of those calls and you start to kind of see a shift in, that's a use case that, we hadn't included as a community, and kind of what we thought an IR should look like. And you start to see sort of the folks behind QIR adapt. Or in some cases, the QIR Alliance, the members of the QIR Alliance have said in calls like that, that's a great use case, but it's probably for a different tool.
Right.
In both cases, it really comes down to that letter I, right, of intermediate.
Yes.
I think one of the things that we've learned over and over again as in a classical computing industry is there's no one tool that can do it all. And that's part of why we talk about non-functional requirements like interoperability and portability. Right. It's part of why we have words like non-functional requirements. So it's I don't think if a particular tool or protocol or format doesn't include a particular use case, that means that use case is bad or uninteresting or useless.
Right,
It means
of course.
we're building a whole ecosystem of tools, and they sit at different points in a stack. Where exactly each thing should sit in that stack, I think, is very much an evolving conversation in the industry as a whole. And I mean, honestly, it's really neat to see that happening and see all the different ideas put forward.
Right. So, I mean, putting the sort of the scoping, where in the stack this should reside questions aside, because I think that is an incredibly interesting discussion. But to return to sort of where you are working in your consultancy, do you see QIR in your work as a way to sort of, aim at the horizon when the customers you're working with can sort of leverage the work you're doing with them to run real quantum programs on a quote unquote real quantum computer at some point in the future, and not worry about the shifting landscape of the lower level of the stack?
I mean, so I think for that, I'll go to, my 3 key takeaways from, Quantum Week this year were a real increasing focus in fault tolerance, looking at where more and more tools can, and more providers and languages, things like that, can have a point of handoff so that, language designers don't have to. Well, there's a talk Natalie Brown gave that, had a really great slide that, what she called the N-to-M problem, right? If there are N languages and M service providers, you don't want to have to write N times M compilers. Right. So I think the takeaway that my second sort of takeaway from conversations, watching talks, and sort of, what concerns do people have at lunch while, kind of chatting about where the industry is really the need for having something like QIR, and that QIR exists now. So, hey, let's figure out the right ways to use it. My third takeaway, of course, was COVID, which is why I've spent the last month.
Mine too. But my unfortunate takeaway.
Yeah, I think it's all 3 of us actually. Yeah,
had almost exactly the same time. Not from each other, I don't think.
My God, but yeah, right. Yeah, a wave hit, we all got it. Yeah.
But so I think somewhere that I am absolutely happy to talk to folks, and offer my services as a consultant is if you're looking to understand what QIR is, where it kind of could fit into your stack, or where the right point of handoff is. That's something where I'm absolutely happy to help have that conversation. The sort of broad takeaway that I can offer, I think is really important is we're looking to, as an industry and as a community, we're looking to really expand what we mean by what a quantum computer is from the state-of-the-art experimental practice of 2017 to what we know a fault-tolerant architecture looks like. And that, we're starting to see that expansion now. There are several entire workshops and tutorials and tracks about that at Quantum Week. And I think the volume of talks and panels about fault tolerance really does speak to that shift as an industry. So with that expansion, we need ways of doing that decoupling, solving that sort of N to M problem that Natalie mentioned in her talk. And there, as I kind of opened with, I think part of the art of building quantum computing out as an industry is being judicious about where we remember the history of classical computer science and adopt it, and where we say, hey, that really isn't the most useful thing for us to carry forward into something that looks kind of different. And something that we really have learned over and over again, we've been bitten by over and over again in the history of classical computer science, is having interoperable formats and protocols allows for decoupling things in really useful ways. If you're a language designer and you have new language ideas, the last thing in the world you want to have to do is sit there and worry about every minute detail of a CPU. Because now you've coupled those minute details and you've reduced the design space for processor designers. And vice versa. If you're a processor designer, the last thing you want to have to worry about is how that affects a particular high-level language. Like, awareness and communication across is absolutely important, but having a coupling where neither side can go pursue their own unique ideas without worry of breaking the other side, that's not an ideal state of affairs. And I think it's not a coincidence that as LLVM has really exploded in the classical computer science world over the last bit over 10 years, we've seen things like Rust come up as a language and very quickly be able to target many of the same backends that LLVM can, and similar languages that are LLVM based, but also that we've seen an expansion of what it means for a classical computer to be a classical computer, that we have seen more use of GPUs and FPGAs and ASICs and going up the stack with things like WebAssembly and, before that, ASM.js. And the fact that we're seeing exploration on both sides of that stack is a result of having a good handoff. So I go to, where do we need to be in quantum computing? We need to expand what our model of a quantum computer is. We need to get better at writing applications. We learn from classical computer science that the way to do that is decouple, so that the people who are coming up with better ideas for applications, the people who are improving the hardware, aren't stuck on, this kind of an end-to-end sort of coupling where we've taken dependencies on things that aren't that expansion.
That's really great.
Yeah, it really is. Thank you for this overview of this highly complicated topic. And I think our audience, they pay such careful attention to these nuances of the developing tech landscape. So thank you for delving in deep on this important topic.
Yeah, I appreciate your time, Cassandra. It's been a pleasure.
It's been wonderful to be here. Thank you so much for having me.
Wow, that was really fun, Sebastian. Good times. I guess, the theme she brought up that was so powerful for me, right, is the immense history of all the tradecraft in computer science and language design and operating system design, and how there are certain elements of that history and tradecraft that have direct and powerful applicability to quantum computation. And then there's other elements where, who knows, there could be brand new pivots, brand new new modalities of expressing that same tradecraft. So, really a cool topic. And I think a valuable one in terms of just seeing with more nuance and depth, right, some of the developments within this space.
Yeah, absolutely. I mean, you put your finger right on why I wanted to have Cassandra on, because it's one of the areas in which I see progress of quantum information science, quantum computing, into this space where it starts to intersect with traditional classical CS and the 70 years of learning that we have in things like compiler design and solution architectures and all the rest of the hard problems that we've been tackling in classical information, classical computing. And more to the point, the modes of productivity, right? Open source software development, the way in which you can marshal the enormous population of very smart people in the world. She mentioned the Unitary Fund being part of the QIR Alliance structure and sort of helping bring people together around the development of QIR. That's just, we talked to Misty from Unitary Fund in a prior episode. Yep. I just think that everything that sort of falls into that space between classical software, open source development, and this new emerging space in quantum information science is the place I find the most exciting to watch.
Fun times, yeah. Really enjoyed that. Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.